Welcome back. In today's lecture, we are going to learn the principles of classical statistical mechanics. So, let me start by explaining what I mean by classical statistical mechanics. As you would know that we have been discussing how to deal with the statistical mechanics or molecular thermodynamics of ideal gases when the ideal gas in the microscopic level is explicitly considered to be comprised of atoms or molecules, and these molecules may be of different types like the heteronuclear diatomic molecule or the homonuclear diatomic molecule. And in each of these cases we saw that there was a specific effect of the underlying microscopic structure of these constituent particles on the measured thermodynamic property of the system. And that was because we could show that the single particle partition function is comprised of a contribution coming from the motion of a structureless particle, which may be an atom, molecule or molecule, and the internal structure of the this particle, which is moving in the volume V at a temperature T for this single particle. Now, the consequence was that for all the thermodynamic properties, we could see that there were contributions coming from the properties of that structureless particle and the contributions coming from the internal structure of each of these particles. Now, when I talk about classical mechanical description, obviously I cannot distinguish between an atom or a homonuclear or a heteronuclear diatomic molecule. It has to be a structureless particle like a billiard ball. So, then in classical statistical mechanics, what we are looking at is essentially neglecting this structural part and trying to formulate this single particle partition function entirely in terms of a structureless ball like particle and how it can be related to the thermodynamic properties like Fu and Cv. Now, if you would remember that we actually looked at the relative contributions of these underlying structure for a monatomic ideal gas in the case of internal energy of a monatomic ideal gas. We found that if I think of the system as being comprised of a structureless ball, then a corresponding contribution of its translational motion would come from u trans, and this u trans is nothing but the energy at a temperature T that comes from the equipartition theorem, and you can also prove that this indeed is so. And the correction term, because of the underlying microscopic structure of the atom, is also given by this expression, and this is dependent on the temperature and the microscopic energy states of the electronic energy levels of the system. Now, what we have done in this discussion earlier, we looked at the relative contributions of u trans and u electronic per atom, and we found that it was only around 1000 Kelvin that some non-zero contribution started becoming important as far as u electronic is concerned. Therefore, if I am looking at behavior of particles at say 300 Kelvin, what I find is the total energy, internal energy of the system is dominated by the translational energy of the structureless particle, and the relative contributions of the underlying electronic structure is very, very small. So, that gives us the first clue that if we are looking at calculating thermodynamic properties of a system at temperatures very close to the room temperature, I can probably neglect the effect of underlying microscopic structure and instead focus on understanding the properties of the microscopic states of this system in terms of only the structureless particle itself. Okay. So, with this idea in mind, let us next go and try and understand how I can model atoms and molecules as classical particles. Sounds totally counterintuitive in the sense that we already know from quantum mechanics that this is not an accurate description. But as I said, at finite temperature, where you are measuring the bulk properties like thermodynamic properties, this kind of approximate description may still be good enough for our practical purposes. Now, we already know that atoms or molecules in a system may be presented as wave packets. Now, when you are at high temperatures like 300 Kelvin, so in that case the spatial extent of this wave packet is small, and this allows us to model each atom or molecule as a structureless billiard ball. On the other hand, there may be problems which are inherently quantum in nature, and in those cases, especially at low temperatures, the wave packets are spread out. They overlap with each other, and the quantum effects start become very, very important, as a result of which we cannot adopt the description of the atoms and molecules as a structureless billiard ball, but we have to resort to the description taught to us by the language of quantum mechanics. So, in today's lecture, once again let me remind you that I am going to talk about the properties of a system which is a bulk system, which is comprised of 10 to the power of 23 interacting particles, and for which we have already developed the necessary framework for describing the microscopic model in terms of quantum mechanics and the macroscopic properties in terms of thermodynamics, and we have seen how the principles of quantum statistical mechanics connects these two extreme limits. In today's lecture, although I am going to retain the same kind of description of the macroscopic properties of thermodynamics, what I am going to do is I am going to describe my microscopic model in terms of classical mechanics. So, all the constituent particles at the microscopic level in today's discussion, they obey the principles of classical mechanics instead of quantum mechanics. Obviously, this is an approximate description, but these are useful to predict thermodynamic properties of systems when we are interested in temperatures such as room temperature. And so, that gives me the purpose of classical statistical mechanics. Now, the very first question when you formulate the principles of such theoretical description, you have to start from the definition of the microscopic state of a system. So, if I have a system comprised of classical particles at the microscopic level, the question is, how do I describe the microscopic state of a system like this? So, let us say that I have capital N particles in a three-dimensional system. So, in that case, its microstate is completely defined in terms of its position coordinates and momenta coordinates. Now, particle 1 has how many position coordinates? 3 in 3 dimension. Particle 2 also has 3 in 3 dimension. So, for capital N particles, I have a total of 3 n position coordinates. Similarly, for each particle, I have 3 momenta coordinates, the x component of the momentum, y component of the momentum, and the z component of the momentum. Therefore, if I consider all the n particles together in 3 dimension, I will be having 3 n momenta coordinates. And therefore, the basic idea is that when I have a system like this, then the microstate, each microstate is specified by attaching a value to each of these 3 n position coordinates and 3 n momenta coordinates. For another microscopic state, they will be having some different values of these 3 n position coordinates and 3 n momenta coordinates. Therefore, in general, we can say that each microstate is a point in the 6n dimensional space that is spanned by 3n positions and 3n momenta coordinates. So, this basically introduces to us the very important concept of phase space, and it is best to use a pictorial description of the phase space to understand what it is. But before I go into that, let me now explain the next concept that we had associated with microstates, and that is the concept of an ensemble. So, in this picture, an ensemble is defined as a collection of state points in the phase space, and I would expect that for a given ensemble, which is defined by a given condition of macroscopic states like a constant volume, a constant number of particles and constant energy, in the case of a microcanonical ensemble, all the state points that I have as the collection of points in the phase space, they must correspond to the same condition of the macroscopic state. So, this is basically an extension of whatever we have learned in the previous part of our discussion in this course. So, now let me take this very simple example of a classical one-dimensional simple harmonic oscillator and try to understand how I am going to define its microstate. So, it is pretty obvious that my one-dimensional simple harmonic oscillator has only one positional degree of freedom, which is given by this position coordinate x, and associated with it there is only one momentum coordinate p, which is defined as mass into x dot, that is the rate of change of x with time. Now, once I understand this, then obviously I would ask the question, what is the phase space of this single one-dimensional simple harmonic oscillator? You have two variables, position coordinate, that is the first variable, and the momentum coordinate, that is the second variable. So, the phase space is going to be a two-dimensional space which is spanned by this single position coordinate x and the single momentum coordinate p, and therefore, I would say that this microstate that I see here, which is characterized by this position coordinate x and momentum coordinate p, in this two-dimensional plane, this is going to be a point in this two-dimensional plane as shown by this red dot here. Of course, this is the simplest possible visualization of the phase space of this single classical one-dimensional simple harmonic oscillator. But of course, as you understand, in an ensemble, we are going to have not only a single point, but it is possible that we are going to have many microstates obeying the same conditions of the macroscopic thermodynamic state. So, let us next see what happens for this particular system when I solve its equation of motion and under the condition that in the macroscopic level its total energy E is a constant. So, basically then how do I visualize the different microscopic states of the system? In this animation, each position of this mass m is one of the microscopic states of the system, and this movie is showing you that this mass is moving and having different values of x at different times. So, this is a representation of the system populating different microstates with different values of x and different values of y. Now, here I know that by my definition this particular mass is under the influence of a potential energy function, which is given as u x equal to half k x s square. As a result of which, here x is the displacement in its position coordinate from its mean position at x equal to 0. Then I would say that there will be a restoring force acting on this particular system, which when the system undergoes a large displacement takes it back to its equilibrium position. Then what we can say is, here I have a representation of the different values of x that can describe the microscopic state of the system with associated momentum coordinate p. Now, once I understand this, then I will try and see this motion in the phase space. Before I do that, I do understand that if I solve this equation of motion, I get the values of x and p as a function of t, and here basically x and p, both of them are oscillating functions, and I have introduced two constants of integration, x naught and b, and omega is the intrinsic angular frequency of the simple harmonic oscillator. Now, what is this telling me? It is telling me that starting from an initial condition which defines my x naught and b, then I can calculate the values of x and p for this system at any given time, right. So, this basically for a microcanonical ensemble where the total energy is fixed will have to obey the condition that I must look at only those values of x and p which obey this condition that x half k x naught square is equal to the given value E, and therefore, x naught is defined by the given value of E, which in turn goes and defines what I am going to have as the values of x and p at a given time, starting with some x naught and b as the initial condition. So, what we are going to do next is we are going to see this collection of microscopic states x and p for a microcanonical ensemble where I have a total energy E fixed, and this simple harmonic oscillator is present in a constant volume and n is equal to 1 by the construction of the very simple system. Then all the microscopic states which correspond to those values of x and p in this microcanonical ensemble are accessible, which obey this condition. So, what I have done is, instead of writing it in terms of k, I have identified that k is nothing but m omega square, if m is the mass of the oscillating body which is oscillating with an angular frequency omega. In that case, this condition can be rewritten using this expression. Now, in this expression, as you see that x naught is the initial condition and x and p are the microscopic state information at a given time. Now, if I look at what happens to the phase space, I understand that all these microscopic states in the phase space, two dimensional phase space x and versus p, all the values of x and p which obey this relation will show me the accessible microscopic states of this system. So, that is what we are going to have a look at next. So, please have a look at this expression. I understand that this expression is telling me what are the possible values of x and p that obey this constant condition of E, where E is a constant, therefore, x naught is a constant for a given system of m and omega. Now, this has a form of x square by a square plus p square by b square equal to 1, and this of course is the equation of an ellipse, and therefore, I understand that I am going to have a plot of an ellipse with axis a equal to x naught and b equal to m omega x naught when I look at the microscopic states obeying this constant energy condition in the phase space. So, depending on what these values of a and b are, I am going to have an ellipse like this, and I am going to have an ellipse like this representing this condition that has been highlighted over here. Now, what does this tell me? it tells me that, let us say that these are the points of origin in the phase space, which is a two-dimensional space in x and p. Now, this is A, which is nothing but x naught, which is dependent on the initial condition. And then I would say that B is this height, which tells me that this is m omega x naught. And for any point x and p which lies on this red curve representing the constant energy surface in this two-dimensional space, is a representation of a microscopic state which obeys the condition that the total energy E is fixed, it is present in a constant volume, and the number of particles is equal to 1. Now, in this case, what we can also say that, well, all points on this red curve are the possible microstates for this given ensemble. So, what is the number of these possible microstates? So, the number of these possible microstates is equal to the number of points present on this ellipse, and obviously that is a very, very large number. For all practical purposes, there is an infinite number of points which are dimensionless quantities that can be populated over this red curve. So, that gives back this idea that we had, that associated with a given macro state, there is a very large number of microscopic states possible for a system, even if it is a simple system like a classical, like a simple harmonic oscillator. Okay? Now, let us go farther ahead and see that for a given value of energy, let me remind you that x naught is fixed. If that is so, then we can ask the question that if I start from some value of b, I mean, let me have a look at this particular point. This particular point is x is equal to x naught and b is equal to 0. That will correspond to this particular point. Okay. Now, there is no reason why any solution x and p of this equation of motion would prefer some particular value of b or the other. As a result, as you see, there is no bias in any of these solutions regarding where your solution x t p t is, or in other words, I would say that all solutions x p of the equation of motion are randomly and uniformly distributed over the fixed ellipse, which has been shown using this red curve in the two-dimensional phase space of this simple harmonic oscillator. So, what is the consequence? Which means that, let me look at these 2 points. Now, in these 2 points, they differ only by the phase. They have the identical x naught values, and you would say that, is there any reason why this solution will be preferred over this solution? I know the solutions x and p at these 2 points, and I find that there is no reason why plus b will be preferred over minus b. And this tells me that each of the points present in this over this ellipse, they are equally probable, and therefore, they have a completely random and uniform distribution over this red curve. Now, when I understand this, then obviously, once you know what the microstates are, the basic idea is I will average over these microstates and obtain the thermodynamic properties. Now, let us say A is a measurable equilibrium property of my system. Then let me remind you, how did we calculate the equilibrium value of this property? A equilibrium will be AI Pi, where I have measured AI for all microstates I with a probability Pi, and I summed them all up, and this probability is the equilibrium probability for the given ensemble. And so, if in my case, if it is a simple one dimensional system having only one position coordinate xi and only one momentum coordinate pi, ai is going to be a function, the value of ai is going to be a function of xi and pi, and then I can measure these values, let us say for capital N points over that constant energy contour in the system. But here, as you see that all the x and p values, if t varies continuously, they can also vary continuously. As a result, we find that it is easier to replace the summation in the classical case by this integration. So, essentially I am doing the same thing. For a given microscopic state, I am looking at this AXP. Okay. Now, for a given microscopic state that is characterized by the coordinate x and p, I calculate what the value of A is. Then I multiply it with the probability of observing the system in that microscopic state when it obeys the constant energy condition, and then I sum over all possible values of x and p, and since x and p are nearly continuously distributed instead of the summation, I do the integration. But as you see that here, when I am evaluating E equilibrium, instead of having a sum over dimensionless of the microscopic states, I am now having an integration over the phase space. So, while this equilibrium value was dependent only on the dimensionless quantity pi, now I have introduced in my discussion the dimensions corresponding to dx and dp. So, obviously, when I normalize this value, I normalize this probability, then there will be some normalization constant appearing here that I have indicated as 1 by c. I have not defined what these things are, rather I would like to highlight that for any such system, A equilibrium is going to be given by estimated value of A at a given microscopic state, and then under the condition that you have only those microscopic states which satisfy this condition, that the corresponding value of energy of the system is equal to the equilibrium energy value that is given to you, and then I integrate over the entire phase space and normalize the summation this integrated value suitably with a constant, and that will give me A equilibrium. So, once I know this, then obviously I would understand that if I have information regarding the microscopic states of the system, I should be able to find out the equilibrium properties, just as I have done in the case of the quantum systems. Starting from the quantum mechanical model of the microscopic state, we could obtain the thermodynamic properties. So, in the next part of the lecture, we will see how to use this kind of concept of having an integration over the phase space to find out the thermodynamic properties in a given ensemble using classical microscopic states. Thank you.